So in the other video I made, I talked a little bit about graphs for angular motion. What I'd like to do right now is take a few minutes to link what we know so far about angular motion with the formula sheet. And so I've got open on my screen here the official equation sheet that gets used on the AP Physics exam. So first up, as a reminder, over here you've got that list of all the different variables that show up on here. And if you look down towards the lower part of the list, you've got angular acceleration. Sorry, that got a little sloppy. You've got theta for angle, and you've got omega for angular speed. All right, I'm just going to get rid of those annotations quick. Now, there are a couple equations that show up on here. So the first two I want to point you to are these right here. Now, something in particular I want to point out. I'm going to scroll up so we can see the top of my formula sheet. I want to look at these two equations right here. Now, if we look at these two, so this one we have x equals x naught, which is initial position, plus initial velocity times time, plus 1/2 acceleration times time squared. Down here, we have angular position equals initial angular position plus initial angular velocity times time plus 1/2 angular acceleration times t squared. Something similar happens with this other equation. We have Vx, which is just your velocity in the x direction, equals your initial velocity plus acceleration times time. Here we have angular velocity equals initial angular velocity plus angular acceleration times time. And so these aren't truly new equations. We're using different variables so that we can represent angular motion instead of linear, but those relationships are still the same. Just like the relationships between the graphs are still the same, where slope of angular position versus time is going to be angular velocity, and where slope of angular velocity versus time is angular acceleration, and area of angular velocity versus time is change in angular position. And so we're able to use the things that you learned earlier this year about linear position versus time and linear motion, and we're able to now apply it to these objects moving in a circle. Now, the other equation I want to point you to is earlier this year we defined the term period. And we talked a little bit about the part of this equation right here. That got really sloppy, sorry about that. Where we talked about the part that's period equals 1 over frequency. Now we can add this middle part to the equation at this point. With angular motion, we can talk about the period as the time to complete one full cycle or one full circle. So in the lab you did with that yellow disk, the period was the time it took your dot to go all the way around once. And then the period is going to be 2 pi divided by the angular velocity. We're usually going to end up doing angular velocity in radians, and 2 pi just so happens to be how many radians are in a full circle. And so this ends up giving us the time it takes to go all the way around that circle once.